All right, so once again, you're seeing this is an improper integral because this time we are evaluating towards negative infinity. This is the first problem we've seen like this, but what does it change? Well, absolutely nothing. So what we're going to do is just let k approach negative infinity, ranging from k to 2 of e to the x dx. So now our integral of this, if we integrate e to the x, hopefully we say, this isn't that bad. E to the x is e to the x. And don't forget, it's the limit as k approaches negative infinity. Let me give myself a little more space. Evaluated from k to 2. So now when I go ahead and evaluate, I substitute my values. This would be e to the 2. Again, notice no limit as k approaches because there's no k's here. Minus the limit as k approaches negative infinity of e to the k. So there we go. So now let's just go ahead and evaluate this. E to the second is, well, that's e to the second. And when I go ahead and substitute this in, this is going to be e to the negative big. And whenever we do that, that's going to be a negative exponent, always drops it down to the denominator. And you may have recognized this from before. Hopefully you're recognizing that e to the something big is something big. And 1 divided by something big is 0. So therefore, the answer to this is e squared. And it converges. All right, so good job if you did that one. Bad job if you got it wrong. No, I'm just kidding. It just takes practice. Okay, so here we go again. That was a little funny. Come on. All right, so here we go. Problem number 8. Take a pause, try it yourself. We've seen stuff like this before. All right, here we go. I'm going to go ahead and say this is an improper integral because I'm substituting in 0, and dividing by 0 in this context would be 1 divided by 0, so it's undefined. So we're going to go ahead and say let this be the limit as k approaches 0, going from k to 2 of 1 over, and if you want to rewrite it, you absolutely could. This is x to the negative 1/2 dx. And that, takes up a step. So now, the integral, the antiderivative of x to the negative 1/2, that's a power rule. So I'm going to go ahead and add 1 to that, which will give me 1/2 divided by 1/2. And just through a little bit of algebra, multiply by the reciprocal. So this is going to end up just being, 2. There we go. And then that'll be evaluated from k to 2. So now let's go ahead and substitute in our values. This is 2 times 2 to the 1/2 minus the limit as k approaches 0 of 2 times k to the 1/2. And what you'll notice is this is working out really quite nicely. We've got, let's see, 2 to the 1/2 times 2, if you wanted to think of this as 2 to the first, it would be multiplying, so you add your exponents, which will give me 2 to the 3/2 minus 2 times 0 to the 1/2. And in this case, we didn't really have to worry about approaching from the right or approaching from the left, because I went from a negative exponent to a positive exponent after my integration, so I'm no longer dividing by 0. So, therefore, this is quite simply just going to evaluate out to 0, which leaves me with the answer of 2 to the 3/2. Now, there you go. That's it. So, a couple more problems. The reason for this problem, do you notice this is exactly the same as the last problem, except you'll notice here I'm not integrating to 0 or to infinity. It just takes a little bit of thought. You'll have to notice, when I evaluate this 2, it's going to be 2 minus 2, which will make me divide by 0. So I actually do have an improper integral. It's that 2. So what I need to do here is let the limit as k approaches 2 be my substitution there. And once again, my bounds of integration will go from 1 to k. Now, you do this problem like normal, just like you would any other problem, right? So you say, all right, to do this problem, typically most students are going to do a u substitution. So therefore du is equal to negative dx, and we've seen this once before. So I'm going to go ahead and say, all right, so we got the limit as k approaches 2, going from, now for my bounds of integration, if I go ahead and use my little translation here, I can substitute in 1. So this is going to be 2 minus 1, which is going to be 1. And then, interesting here, I'm going to substitute my k, so this is going to be 2 minus k. And that's okay. You see, it's still, you can see, it's still that dividing by 0, because it's going to be 2 minus 2 when we evaluate the limit. So it looks a little funny, but it all works. So now this is just going to be left with 1 over the square root of u, negative du, because of the negative dx right there. So when I substitute in the for dx, it's negative du. Okay, so you can go ahead and use your comfort, however comfortable you are with doing integration. I'm going to just do this a little slowly. I'm going to go ahead and rewrite this as negative u to the negative 1/2 du. So now for this integral, this should look familiar. This is very similar to the last problem we just did. The limit as k approaches 2. And I'm going to add 1 to my exponent, which would give me, which would give me u to the 1/2, well, negative and negative from up front follows along. So it gives me u to the negative 1, or sorry, u to the positive 1/2 divided by 1/2, which is the same thing as just multiplying by 2. And for my bounds of integration, I have 1 to 2 minus k. And the nice thing here is I don't have to go ahead and sub back in what u is equal to, because I changed all my numbers. So therefore, I can just sub in with what I have right here. So I'm going to have negative 2 times, the limit as k approaches 2 of negative 2 times 2 minus k raised to the 1/2 minus negative 2 times 1 raised to the 1/2. And now when we evaluate our limit, we say, can I just substitute in 2 into k? Absolutely. 2 minus 2 makes 0. The square root of 0 is 0. Times negative 2 is 0. So I just end up with 0 minus the square root of 1 is 1. 1 times negative 2 is negative 2. Times a negative, so it's a positive. So it's just positive 2. Fantastic. So there we go. 2, and it converges. Fantastic. All right. So there's that problem. Using a little bit of u sub, no problem. And last but not least, looking at this problem, you can hopefully identify, all right, the 0, is this a concern for us? Well, no, the 0, I'm not dividing by 0. This is defined. The infinity is the problem. So that's where we're going to use our limit. We're going to say the limit as k approaches infinity of 0 to k of x e to the negative x dx. All right. Now, how do we do this derivative? Well, substitution, I'm not seeing a great sub. How about instead we use by parts? I can let the thing I take the derivative of, u, be equal to x, and the thing I take the integral of, dv, or v prime, whatever notation used in your class, dv, which would be e to the negative x dx. So I take the derivative of this. So this would be du is equal to dx, and the integral of dv would be v. The integral of e to the negative x would be e to the negative x divided by negative 1. If you need to see that slower, you could go ahead and think of this as just a side little problem and say, all right, I'm integrating e to the negative x dx. I'm going to use a little u substitution at negative x. So therefore du equals negative dx. And you could work the problem, and you'll see that's your answer. Okay. So there we go. So now we're doing a little by parts, which is fantastic. No problem to us. So what we will do is we'll go ahead and say, all right, it's my diagonal. It's x times negative e to the negative x. Going to be evaluated from 0 to k. So because there's going to be k's in here, we need to include the limit as k approaches infinity. minus the integral, now for the bottom part, right? So this is going to be negative e to the negative x dx, evaluated from 0 to k. And notice, because we didn't use substitution, we still have x's in our problem, so I don't have to worry about my bounds. They didn't change. So we just keep going with the problem. And if you wanted to evaluate this right now, you could, or if you want to save it till the very end and evaluate all of your integration boundaries all at one time, you can. It's just personal preference. So I won't evaluate yet. I'll just leave it as is. So now what are we looking at here? We have, excuse me, the integral of negative e, well, in this negative I could bring it out, right? So negative into a positive. So I'm just doing the integral of e to the negative x, and as we said before, that's e to the negative x divided by negative 1, which would then change this whole thing into a negative again. Okay. And then evaluated from 0 to. Okay. So here we go. We're going to go ahead and now start evaluating. So when I substitute in my k, I'm going to get the limit as k approaches infinity of negative x, and to take care of this negative exponent, sorry, not negative x, negative k, and I'm just going to write it down here in the denominator, just like that, just to help us see it. So this is negative k divided by e to the k minus, now what? We're going to go ahead and substitute in our 0. Right? So this is negative 0 times e to the negative 0, or I could drop that down to the denominator, but the big idea here is 0 times anything makes 0. So this piece here takes care of that whole evaluation. So then minus, now taking care of our next part, the limit of k approaching infinity of e to the negative k, or that would be the same thing as 1 over e to the k, minus, let's see here, yeah, minus e to the negative 0, but e to the 0 is 1. There we go. And we set forth now evaluating our limits. So let's go ahead and substitute in here. We're going to have something negative big divided by e to the big. Ooh, that's an interesting scenario. Minus, let's see, the 1 over e to the big minus 1. And then this again. Okay, so there's an interesting predicament here. What is something big divided by something big? And there's something you would learn in a following calculus class called limit. It would be convergence tests and divergence. You test for convergence and divergence, and there's all these different tests. And there's one we could use here. Or in MAT212, we teach you about this thing called L'Hopital's rule, which says in this exact scenario, there's a little bit of calculus you can do to check to see what's happening here. So the good news is I won't give you something like this on your test to have you figuring out what's actually happening here. I was really just picking the problem because I wanted you to go through all this thought process. So I'll address this piece in 1 second. So let's just finish up this piece over here. 1 over something big makes 0. So I think everybody can agree, you guys can all agree that what we're dealing with here is negative something big over e to the big minus a negative 1 makes plus 1. So the question to be able to figure this out is, what does this little piece do? And I'm going to do a very, very quick version of L'Hopital's rule. L'Hopital's rule is awesome. L'Hopital's rule. What L'Hopital's rule says is really simple, and you do not need to know this for this class, but I'll just do it real fast just so you can see it. What L'Hopital's rule says is if you have infinity divided by infinity, or 0 divided by 0, then what you can do is do the derivative of the numerator and the derivative of the denominator, and that limit is equal to the limit we had before. So the derivative of negative x would be negative 1. The derivative of the denominator, e to the x, would be e to the x. And so now what L'Hopital's rule says is we can go ahead and substitute into here. And this answer is the same as the one we had before it. And what we can all agree on now is this is 1 over something big, which means it's equal to 0. So therefore, and again, you don't need to know that for your test, but the big idea here is we just got 0 plus 1, so that means the answer is 1. It converges. Just wanted to expose you to kind of an interesting problem where we had to use a little bit of by parts. And again, you won't have to use the L'Hopital's rule on your test, but good for you to see, good for you to grow as a human being and a mathematician. All right, so thus concludes, yes, there's no more problems, thus concludes improper integrals. So the big ideas, identify what's making you divide by 0 or what's making you approach infinity. Let that thing be your limit as k approaches that number, and then do your integration like normal. Finish up with a little bit of limit rules, and if you converge, you're going toward a number. If you diverge, it means you're going towards infinity. Okay? Best of luck.